Okay, so we have a few questions or two questions from previous lecture and tutorial 6. Okay, the questions we solved are about force excitation. Okay, most of them are about spinning damper system, except the question number 3. We need to derive the equation of motion. Okay, question number 6. When an exhaust fan of mass 380 kg is supported on springs with negligible damping, the resulting static deflection is found to be 45 millimeter. If the fan has a rotating impedance of 0.15 kg/meter, find the amplitude of vibration at 1750 RPM and the force transmitted to the ground at this speed. Okay, so the system is a spring mass and subjected to imbalance. This has two parts. First of all is the free vibration is given, like static deflection is given. And from the statical deflection, we can find K, or you can find omega n. Okay, so you can find omega n if you want. G over delta. Delta is 45 millimeter. We convert to meter. So this will be square root of 9.81 divided by 45 times 10 to the power minus 3. And you can calculate omega n. Omega n is also equal to square root of K over n, and you can find K as well. Okay, we will need K. So this is the system. The rotating impedance is 0.15 kilogram, which is ME. Kilogram meter. And the speed is given omega as n equal to 1750 RPM, which is revolution per minute, from which we can find omega. Okay, 2 pi n over 60 to convert it to radian per second. So the amplitude is x equal to ME over capital M, total mass, times R square, which is the frequency ratio, divided by square root of 1 minus R square, whole square, plus 2 zeta R square. So this is the amplitude of the rotating impedance. Here we have no damping. As mentioned, that damping is neglected. So you put zeta equal to 0. And this will reduce to R squared, or it is ME over M over 1 minus R squared. ME is given, the total mass is given 380 kilogram, and R is omega over omega. And that will give you the answer to the question. Okay, 0.15 divided by 380, and the frequency omega is, we need to calculate it. So the rest is you can do. The second part, this is part A. Part B, the force transmitted to the ground at this speed. We talked about the force transmitted at the beginning of the tutorial. The force transmitted is the spring force plus the damper force. Since here we have no damper force or no dampers, and the damper force is 0, the transmitted force will be only K times X. That will give us the amplitude or magnitude of the transmitted force. So part B, Ft will be only K times X. That will be the force transmitted from the machine. The machine has imbalance. And the imbalance force is F naught. You can calculate ME omega squared. And Ft, how much of that is transmitted to the ground? is calculated by the spring force. So you can compare with F naught. Okay. We have a dedicated section for the transmitted force, and we call it vibration isolation. We will talk about that. Okay. Question number 7. An electric motor weighing 750 pounds and running at 1,800 RPM is supported on 4 steel helical springs, each of which has 8 active coils with a wire diameter of 0.25 inches and a coil diameter of 3 inches. The motor has imbalance weight of 100 pounds with its center of mass located at a distance 0.01 inch from the axis of rotation. Find the amplitude of vibration of the motor and the force transmitted through the springs to the base. Where we have the weight is given, and we have N is given, RPM, and K is, we have 4K. This is, we need to get K equivalent. All of them are of the same, specifications, characteristics, each of which has 8 active coils. So we have N equal to 8 with wire diameter, which is small d, equal to 0.25, and a coil diameter, which is capital D, equal to 3 inch. And it is made of steel. Okay, you can calculate K of the spring using G d to power 4 over I think it was 64 N R to power 3. We can check from tutorial number 1. Tutorial number 2 in the table. Okay, this is the GD to power 4 over 64 N R to power 3, which is, I think, put it correct. Yeah, GD to power 4 over 64 N R to power 3. R is equal to D over 2. This is the coil radius. And N is 8, D is 0.25 inches, and G for steel in pound per square inch. We need to find it from tables. I think it is 11.2 maybe, times 10 to the power 6. So we need to find how much is G in pound per square inch. Okay, and then this way you calculate K for each spring, then you get K equivalent, which is 4K. And this is an dam system. We have where unbalanced weight is 100 pounds. This is the small m is 100 divided by G. Okay, and also the eccentricity is 0.01. Okay, you can take G for inch per second square, so 386, and then you can calculate the amplitude of vibration from the same equation of equation number 6. This is N-dam system. After that, also requires to find the transmitted force through the springs. So it will be K equivalent times X. That will give us the transmitted force, because the only element separating the machine from the ground are the 4 springs. Okay, so this is the tutorial number 6, and we can move to lecture 7. Okay. Okay, this is the 3rd type of excitation that we will cover in this chapter, and the last part, the support motion. In the support motion, it means you have a system that is modeled as spring mass system, maybe damper with damper on the ground. The ground is shaking or vibrating, and that vibration will propagate to the mass through the spring and the damper. If you have the machine without the spring and damper, it is rigidly attached on the ground, it will take the same vibration of the ground, 100%. But if you put spring and damper, then the transmitted vibration to the mass, it might be lower and it might be higher. It depends on the values of the spring, and it might be the same. The three cases are possible. Okay, so not any spring and damper system will make the isolation or reducing of the vibration. Some will cause resonance, and resonance, the vibration will be higher, very high. So there are three possible cases that, but when you remove the spring and damper, and suppose we have a machine, okay, supported by nut and bolt, okay, and this. Okay, so this is the ground, okay, and this is vibrating with Y. The machine will also, if you take the vibration of the machine, is X. So if you have rigid attachment, we'll think that X equal to Y, because there is no any elastic member between the machine and the ground. But when you put the machine and fix it with spring and damper, and this is the ground. Okay, so I just assume it is the model is just a mass. Then if this is vibrating with Y, this will vibrate with X. X will take, depending on the values of K and C, might be less than Y, might be equal to Y, might be greater than Y. All the three cases are possible. Okay, so there is a case, in fact, there is X equal to Y. We will see how. We'll talk about how to calculate the spring of the force in this case. All the previous cases that the spring ends are both, at least one of them is fixed with the ground. Here, or not moving. Here we have both ends of the spring are moving. So to calculate the spring force or the damper force, we will use Hooke's law, which is K times the change in length. We used to call it X, but now it is not X. So if you have a spring, if this is L0, which is unstretched length, or undeformed in general, it might be compression spring. Okay, position or state. Then if the lower end is moving with Y, so this point will come here, and the upper end is moving with X, so it will come here, and the spring will, assuming that X is greater than Y. So this point is moving with Y, and this point is moving with X. Then the new length of the spring is L. So the change in length, delta L, is L minus L0. Okay, the total length L is going to be L0 plus X minus Y. Right? This is L. You compare the two figures. you will see that L is equal to L0 plus X minus Y minus L0. So as a result, you will get X minus Y. That is delta L. And the spring force is K times delta L. This is Hooke's law. So it is K times X minus Y. Here we are assuming X is greater than Y. This assumption is going to be helpful to determine the direction of the force. Because the spring can be either under tension or compression. So you stick with one assumption, and then the true values of X and Y will determine whether it is under tension or compression. And the same thing we can do with the damper. The damper force is Fd equal to C times X dot minus Y dot, because you need the velocity, and X minus Y is the displacement. And you take the derivative with respect to time, you get the velocity. So the damper force is going to be C times X dot minus Y dot. Okay, this is the model. We have the mass, which is now assuming a machine, and the base is moving with Y. We will assume for simplicity and within the scope of the course, this is sinusoidal. Okay, that is Y equal to capital Y, which is the amplitude of the base motion, sine or cosine omega t. And the free body diagram is as shown here. We have the spring. When you assume X greater than Y, the spring will be under tension. So its force, the direction of the force is downward. The spring is under tension, it means it is elongating, and then its effect on the mass is pulling the mass downward. And the same thing with the damper force, it is pulling downward. Okay, so the spring force is Kx minus Y, and the damper force is Cx dot minus Y dot, and there are no other forces. The weight is cancelled by the static equilibrium equation, comes from K times delta. So we don't put the weight. And then we apply Newton's second law here. Sum of forces equal to mx double dot. The mass is moving with acceleration equal to x double dot. So when you do that, you get mx double dot equal to minus kx minus y minus c times x dot minus y dot. You can proceed this way. Okay, let me just make the equal sign and distribute the, in the bracket, we get minus kx minus cx dot plus ky plus cy dot. And when you take in a y and y dot should be known. Those are known quantities. When you put the x term that contains x and x dot to the other side, we get m x double dot plus cx dot plus kx equal to ky plus cy dot. And if this is sinusoidal, this will be k times capital Y sine omega t plus c times capital Y times omega cosine omega t. You know, the solution, to find x, you can use the principle of superposition. You find the solution due to only the sine term and call it x1, and then you find the solution due to cosine term only and call it x2, and then you can add them together. This is one approach, but this is very lengthy. The second approach, which might be also helpful, so we use relative displacement. Is it? which is x minus y. And you can differentiate both sides, you get z dot equal to x dot minus y dot. And the equation becomes mx double dot. Instead of x double dot, you will put z double dot plus y double dot equal to minus k times z minus c times z dot. And then the differential equation will be in terms of z rather than of x. Okay, this way. So it is mz double dot plus cz dot plus kz, and we'll move y my double dot to the other side becomes minus my double dot. Y itself is sine capital Y, which is the amplitude of the base sine omega t. The amplitude is measured from 0. So here is Y. Okay, not from peak to peak, from the 0 to the maximum. And when you differentiate it twice, you will get minus omega square y sine omega t. A minus and minus becomes plus. Now this equation is in z, not in x. You can solve for z, which is the equation is identical to the rotating imbalance. The rotating imbalance was m omega squared e sine omega t. So this has the same solution of, but that was x, not z. In the rotating imbalance, the equation was about is in terms of x, not in terms of z. So we have energy here that is z replaces by x, and m omega square y is replaced by me omega squared. So you can get the same solution. So z, which is the steady state solution, here the homogeneous is as we discussed in chapter 2. The particular solution is the most important solution in vibration. That after sometimes only the steady state solution will be existing or remains. So z equal to z sine omega t minus phi in the same form. And we have the sign on the right hand side of the differential equation. We use sine with phase because there is damping, so there will be phase, and depends also on omega over omega. Z is the amplitude of the relative motion. It's going to be sine wave, and Z is the amplitude. The amplitude of the relative motion displacement is m omega square y over square root of k minus m omega square or square plus c omega square, and the phase is tan phi equal to c omega over k minus m omega square, which is as we did before. We can divide by k, you will get here y, and this will be omega over omega n squared divided by the square root of 1 minus omega over omega n squared all squared plus 2 zeta omega over omega n squared. You can put it in dimensionless form as we did in the force excitation and the rotating imbalance. The same thing with the phase. Okay, now we need to go backward to find x. So we substitute in x equal to z plus 1. And this will require some math. We will use some trigonometric identities to reach to the final equation. Okay, this is all math. You cannot add, but we have to bear in mind that x equal to z plus y. When you add them together, you will see there is difference in phase. So you cannot add z plus y, the amplitude of z plus the amplitude of y. So when you substitute for z, this will be capital Z sine omega t minus phi plus capital Y sine omega t. So we cannot say this is z capital Z plus capital Y because there is phase difference. If this is sine, if phase is 0, then you can add them together. But here the phase not necessarily is 0. So what you can do is use the expansion of sine omega t minus phi to sine and cosine. So this would be sine omega t times cosine phi minus cosine omega t sine phi plus y sine omega t. And you can proceed until you get x sine omega t minus psi, not phi, some other phases. Then the phase phi was between z and y. Here psi is the phase between x and y, so they are not the same. Here he gave an approach using the complex harmonic motion, which is ei omega t, and the procedure is the same. Okay, the final equation, all this is math. I will not go through. What we need is the final equation. The amplitude x, that at the end we will get x equal to, as I gave you there, is x sine omega t minus psi. Okay, I will repeat it here. Okay, where the capital X is the amplitude of vibration of the mass, the absolute. Z is the relative. X is the absolute measured from fixed reference. So we get amplitude ratio x over y equal to square root of k squared plus omega c squared o divided by k minus m omega squared or squared plus c omega squared. And also you can get this in dimensionless form, which is 1 plus 2 zeta omega over omega n squared divided by 1 minus omega over omega n squared all squared plus 2 zeta omega over omega n squared. Okay, and the phase is tan psi equal to mc omega to power 3 divided by k multiplied by k minus omega squared plus omega c squared. Here at resonance, phase is the psi is not necessarily equal to 90 degrees. It depends on zeta. Okay, because if at resonance this term will be 0, but we will have mc omega to power 3 divided by omega c to power 2. So there will be c here or zeta in the equation at resonance. This will be not necessarily equal to 90 degrees. Okay, so let's see the plot of x over y and psi or psi. This is x over y versus the frequency ratio for different values of zeta. For different values of zeta, here it is shown with zeta equal to 0.05, 0.1, 0.15, 0.25, and so on. And you can see there are clearly two regions that x over y is greater than 1 from 0 to square root of 2. Here x over y is greater than 1 and equal to 1 at square root of 2 regardless of zeta. All the curves will meet here. And we have the second region is x over y is less than 1. So the three cases I mentioned that x can be greater than y, can be less than y, can be equal to y, are very clear here. And within the range from 0 to square root of 2, where the resonance exists and the peak also exists. This could go to infinity if it is at resonance when there is no damping, and can be very high if damping is very low near resonance. Okay, and the one way to get the isolations or to get the transmitted vibration to be less than the base is when the frequency ratio is greater than square root of 2. So not any damper and spring will make the vibration propagation reduces less than 1 or become less than 1. It might be bigger than 1 because this is a vibrating system. Well, once you put the spring and the damper, you are putting elastic members between, and you could expect that the vibration can be higher than the base. Okay, so it should be greater than square root of 2, and this will be based on K and M as well as on C. Okay, the frequency ratio will be omega over omega n, omega n square root of K over n, and as you can see with damping, this will be there will be variation, but the effect of damping at very high frequency is negligible. Okay, with the small zeta, with high zeta, they will merge. Okay, so those are the observation. It should be observed that the amplitude curves for different damping all have the same value of x over y equals to 1, and the frequency ratio omega over omega n equal to square root of 2. So this is the point at which it will have the transition. Before this value, x over y is greater than 1. Above square root of 2, x over y is less than 1. At square root of 2, x over y equal to 1. Okay, well, examples of base excitation is a car traveling over rough road. The road is not vibrating, but since the car is traveling with a speed, the tire will follow the profile of the road, and the tire will give excitation to the car. So you take the tire of the car as a rigid member or rigid wheel, and the spring and the damper of the suspension is located between the tire and the body of the car. So the tire is going to be it's going to follow the profile and give excitation as y. It will take exactly the same motion of the profile of the road, but the car its motion will be calculated from base motion. So let me read the example. Take 3 minutes. Okay. The figure shows a simple model of a motor vehicle that can vibrate in the vertical direction while traveling over a rough road. The vehicle has a mass of 1,200 kilograms. The suspension system has a spring constant of 400 kilonewton per meter and a damping ratio 0.5. If the vehicle speed is 20 kilometers per hour, determine the displacement amplitude of the vehicle, which is x. Yeah. The road surface varies sinusoidally with an amplitude of 0.05 meter and a wavelength of 6 meter. Again, in order to be within the scope of the chapter, we will assume that the road is varying as a sine wave. Okay, so it has wavelength is the length of one cycle from peak to peak. That's called wavelength, L. And the amplitude is y. So here, as you can see, from peak to peak, from here to here is called L, or from any point to the next point, that will be L, the wavelength. The y is measured from 0, this is y, the maximum. Both are given. So what is missing is omega. When you have a car traveling over a road, there are two parameters affecting the frequency of excitation. One of them is the speed, the other thing is the L. Why? Because definition of frequency is cycles per second. So how many cycles tire will cover per second? And that is meter 1 over second, right? So a meter per second is V, which is meter per second, divided by L will give us the frequency. So V, if it is in meter per second, and the length, wavelength is in meter, then you get 1/2, which is cycles per second. Yeah. So this is F. Or if you want omega, omega is 2 pi V over L. You multiply by 2 pi to make it radian per second. But make sure that you have a consistent unit, that velocity is in meter per second and L is in meter, then you get radian per second. So for cars traveling or any vehicle traveling over rough road, the frequency is calculated from this equation, omega equal to 2 pi V over A. Okay, we have all the information. Omega is 2 pi F equal to 2 pi V. He did the conversion because he's entering V as kilometer per hour. So he did the conversion within the equation. And this is 1/L. Okay, so it becomes 0.29 times V. So omega becomes, at the speed, is 5.81778 radian per second. The natural frequency of the vehicle is square root of K over M, as usual, because the car is assumed as a simplified model as a single degree of freedom system. We know that the car has 4 tires, but when you neglect the amount of rotation in the car and you assume only the vibration to be vertical direction, which is bouncing, neglect the tire stiffness. Not the stiffness is infinity for the tires, but like rigid, then become single degree of freedom system. Okay, so we will come back to this example next time, and we can do tutorial 7 next time as well. Okay, so I will. We will need a quiz. Let's say Sunday is okay. Sunday or Monday. Okay, so we finished tutorial 6. We can take a quiz in tutorial 6. If I say Thursday is okay, because يعني لسه هاي الأسبوع صعب لا. اوكي يكون بعيد كل سنة. أنا بعطي على كويز على توتوريال 7. كم كويز ناخذ كامل؟ أحتاج الحين آخذ 2 more before the test 2. Okay, so no problem. We can make it next week, Thursday, no problem. I think we have a chance. Okay. Let me send the results for the quiz. ممكن دكتور الكويز اللي يصير الكويز الرابع ناخذه مثلا قبل التست بيوم يومين. ايه قاعد اقول في مجال من كذي قاعد اقول لك اوكي.